This session is billed as a technical session. Don't ask me why. But the real secret purpose of it is for co-sponsors to tell both of you what it is that we do. And the co-sponsors that are represented this morning are the World Space Foundation, represented by Staehle, the Planetary Society of Song and Legend, represented by Charlene, who is playing the role of Blue Friedman as Spot the Wonder Dog. And I'm Maryniak from the Space Studies Institute. And because they printed me first on the schedule, I get to go first. So I'd like to tell you a little bit this morning about the Space Studies Institute. How many of you are members of the Space Studies Institute? Why are you here? Okay.
I want to hear about the competition.
Good, yes. The Space Studies Institute is a operation that has now been going as a nonprofit corporation for 13 years, based in Princeton, New Jersey. Our goal, maybe we could drop the light, please. Our goal and our dream is the use of resources from space to do two things: to provide for the benefit of people here on the Earth, and to open the high frontier of space and broaden the ecological niche of humankind. We want to use resources in space for reasons that all of you know by now. Good morning. Bring it in. We need it. This may be one of our less formal sessions. That is, all of you know by now that our thinking is that we should use resources already in space rather than bring things from the bottom of the Earth's deep gravity well or anybody else's deep gravity well, like Mars, for example. We're doing projects in space. And to that end, we've been engaged for actually longer than the Institute's existence in a series of research programs and education and outreach programs that I'll briefly go over this morning. This is a time scale of SSI's research, and if you haven't picked them up, come up to the second floor, and then you can actually read it, because this is as good as it gets, that's right. But some of the areas of SSI research are things like system studies. What's the big picture? How do all the pieces fit together? And SSI has been engaged in a number of these over the years, gradually refining our plans for the expansion of humankind into space. We also conduct conferences where we bring together the family of researchers around the world interested in working on the use of space resources. And these conferences have been going on since 1974 at Princeton University and have now been compiled into volumes by the AIAA, which co-publishes them with us, and by the AAS as well, which ran one of our conferences. And they're available, and they form basically the backbone of the field of non-terrestrial materials. In addition, SSI is engaged in building and testing real hardware to develop the tools that are necessary to use these resources. One key project, and SSI's first major research project, was work on the feasibility of mass drivers, electromagnetic launchers, for getting material out onto the plateau of free space from places like the moon at very low cost. SSI built 3 of these machines, one at MIT and 2 at Princeton University. And we continue to work on mass drivers, and in fact we're working now with, in cooperation with some of the folks at Sandia that have a cousin of the mass driver, which they call a coil gun. And in our own machines, we've gone from accelerations of about 30 gravities to over 1,800 gravities, sufficient to reduce the length of the machine from 5 miles to about 500 feet. And we believe there's a lot more that can be done in that direction.
These are actual machines?
Those 3 are actual machines. Now, one of the most important things that we think should be done, and in this, I think all 3 of the groups represented this morning are in agreement, is that we need to learn a lot more about the solar system around us and what resources are available to us. We basically need to prospect in the solar system. And we're particularly interested in learning a lot more about the moon because it's close, it's convenient, and we know that our knowledge of it is very, very thin. So we want to complete the lunar chemical map. And we also are very interested in the asteroids. And all three groups represented this morning have some projects going on with respect to asteroids or have in the past. Our key prospecting project right now is what we call Lunar Prospector. And SSI is just a few weeks away from the critical design review, final design product of the project, which is designing an actual lunar space probe to go into low orbit around the moon and polar orbit, and try to answer the question of whether or not there are volatiles trapped as ice at the lunar poles, and complete the chemical map of the moon. And as most of you know, NASA has agreed to give us the gamma ray spectrometer shown at the top of this somewhat cartoony slide, which will be the primary instrument for sensing materials available on the moon. We're also working this summer on a project in cooperation with International Space University, which I'll talk more about in a minute, which we call the International Asteroid Mission. And it's basically a two-part project. It's looking at search methodologies, both from the Earth and in space. It's a survey of all the search methodologies with the eye toward coming up with some optimal ones. And the other part is to look at a human exploration mission or human exploitation mission to use asteroid resources. Now, we know about the chemical composition of average moon soil, and SSI has been working for a number of years on techniques to get the various slices of the chemical pie from lunar material. We started in this field by working with Bob Waldron from Rockwell International, and under contract to SSI, Dr. Waldron proved out the previously unknown steps involved in what's called the hydrofluoric acid leach technique, which gets you all the slices of the pie, but it's very complicated. We've subsequently been working on simple techniques, like physical processing techniques, to get materials like glass to build composites, like beam shown at the bottom, which is a terrestrial composite, which was designed for the solar power satellite studies in the late 70s. But the same machines that can extrude those beams in a continuous fashion can do that with glass composites, wholly made of lunar material. And just a few miles down the road from us is a pair of these solar concentrators, and this picture doesn't really show the size of them. They're 10 meters across. They have 10,000 suns concentration. You can melt ceramics with these things. And we have replaced one of the Stirling engines at the focal point of one of the concentrators with a crucible built by Alcoa, the Alcoa Tech Center in Pittsburgh, and lined with platinum rhodium alloy. And we're using that as the first stage in the first lunar scale, our first pilot scale lunar process plant to make lunar glass. And this will be fully up and running by about midsummer. We're also, by the way, working on other simple processing techniques, and our most recent project is a lunar magma electrolysis project where we're melting soil and basically using electrochemical techniques that are sort of used in the aluminum industry, for example, to get oxygen and other materials from lunar soil. Fairly simple compared to wet chemistry techniques, but there are lots of challenges, like what do you make the electrodes out of so you don't have to continually replace them? What sort of refractories are necessary for the vessels to contain the melts? Another type of space resource that we're very interested in is one that's a man-made resource, the Space Shuttle external tank. As you know, every time the shuttle flies, it takes these tanks to about 98%, in fact, in some cases more, of orbital velocity. And in fact, the shuttle purposely has a MECO, a main engine cutoff, such that the tank will not achieve orbital velocity, because NASA does not have a plan to save and shepherd these tanks. And they're so large, they have such a large cross-section, that they will come down unless people do something about hurting them in space. But there's 53,000 pounds of aluminum in each one of these tanks, and about on average 10,000 pounds of residuals when they're released. So they're a tremendous bonanza, and we're looking at ways to use them. This is just a quick picture inside must be the hydrogen tank, looking aft, and just to give you a feel for the size of these things. They're interesting as volumes, and various people are now looking at and working on ways to use the volumes for habitats and such in space. And I'm happy to announce today that the Institute is working on a project with the Air Force, specifically the Air Force Institute of Technology, for the engineering of a system which can consume external tanks and convert them into feedstocks for space construction projects. It's a brand new project underway at Wright-Patterson Air Force Base. Now, we're also very interested in lunar surface operations, and we have for a number of years been working on lunar mining techniques. A lot of people were writing about them, and we decided to get down and dirty and try some. And in fact, we had some young interns come in and work with us in effect, a big lunar sandbox at Princeton. And we said, design some buckets for a lunar dragline system. And the modern engineering students, some of you are probably modern engineering students, they said, okay, great, where's the computer? No computer. Roll of tin, snips, pop rivets, various and sundry other tools. Build 3 buckets and test them before lunch, and we'll buy you lunch. So we've been doing some of that sorts of work, and we're working with the University of Maryland, where some very sophisticated but modest work is underway to learn about basic lunar excavation. We're working with real simulants compacted to actual lunar conditions. There's a great deal of just basic grunt work that needs to be done to understand how to dig trenches on them and how to loosen up the soil. And that work's underway. And one project that's a lot of fun that we've been engaged in for some time is lunar teleoperations. There's a myth running around the NASA community that because teleoperations is so difficult in space station, which is in low orbit, that you've got to go through several bounces on TDRS to talk to it at various places, and the various systems that are used to communicate have buffer times that they put into the system, that the NASA myth was that, among a lot of people, was that a lunar teleoperation must be impossible because it's so terribly tough, so close to the Earth in low Earth orbit. It turns out it's easier at the moon, and we've shown that it's so simple that even heads of companies can do it. And in fact, a real cute version of this kind of equipment has just become the centerpiece of a space exhibit at the Franklin Institute in Philadelphia. They have a new Futures Center, and it incorporates 2 workstations in a space station mock-up, just because they have to put something in the space station mock-up, where visitors to the Franklin Institute can try operating lunar equipment in real time with the simulated time delay. SSI has always been interested in human habitation in space on the plateau of free space, and our work on space colonies has continued. And although we don't talk about it as much as these projects, because we've come to believe that the large-scale human activity in space would be a logical follow-on once has an economic reason, like space solar power, for example, for lots of people to be there, we have continued to work on some of the details of space habitats, in particular things like human rotation tolerance, very important for knowing how small you can make a space colony. In fact, a lot of the things we're working on now are in this area are aimed at seeing what's the smallest thing that you might call a real space habitat, where people can stay more or less permanently. Because of the pivotal importance of space power, both because it could be the equivalent of the spices and gold that drove people in Europe to explore the Western world, we think that it's one of the most important projects that's going on now. Furthermore, it's a basic enabling technology for everything that we do in space. The space station is grossly underpowered at 75 kilowatts, and we need to shortly, almost immediately, have megawatt scale power in low Earth orbit, and we clearly need it for lunar operations, and it would be delightful to have it for going out into deep space. It would be nice to have the ability to transmit megawatt and gigawatt eventually scale power to spacecraft, cut down travel times from going out to the planets, and do a lot of other useful things. So space power is a main line of activity for SSI. And some of our projects have included looking at how to design solar power satellites from the very beginning so that they use non-terrestrial materials to the greatest extent possible and minimize the amount of material that has to be launched from the Earth. And those studies have been very successful. And we've now gone to the next level of sophistication, which is to say, instead of looking at all lunar resources as being equally accessible and usable for these kind of projects, we're saying what kind of SPSs can you design which use first the simplest forms of non-terrestrial material. We're also looking at a lot of steps between space solar power satellites, bringing terrestrial power to the surface of the Earth, and the present time. And we believe there are a number of very exciting and commercially viable projects and products which can both help us to bootstrap getting out into space and can provide a huge enhancement of capability for lunar bases, space station, and everything in between. SSI is also very much involved in outreach and education. And in education, we range from working with graduate students, both at SSI and in places like International Space University, and this is a scene of some more teleoperated robot experiments going on at the first ISU, International Space University, session at MIT in 1988. ISU was founded by 3 senior associates of the Space Science Institute, Peter DeMandis, Todd Hawley, and Bob Richards. And since its inception, in fact, since before its inception, SSI has been involved with it. In fact, we're one of the voting members of the ISU family. And we are very proud to continue that association. We have worked with ISU in Strasbourg, France last year. I will be the managing director of the Toronto session at York University this summer. And in the next 2 years, I would invite every one of you to find out more about the Institute. Go up to the second floor. They'll be around until about noon, next 1 o'clock today.
Where my name was Charlene on Saturday afternoon. I've changed a little bit, at least my name has. So I'm going to spend just a few moments on the asteroid project and then go on to some of the other things that we're doing at the foundation. That is Eleanor Helene, the principal investigator for the asteroid project, the recipient of most of the support that goes into that project, and I might point out that a significant fraction of that support comes from the Planetary Society, for whom we'll get in a few minutes here. Many of you have probably seen in the news Comet Austin lately. You'll be seeing more of it. UPI just picked up this picture. I don't know where it's been yet. I think they just picked it up about 6 or 7 days ago. The tail actually, in the most sensitive images, extends quite a bit beyond the image there. If we were anywhere near it, it would be a really spectacular comet. Unfortunately, it's not coming close enough to the Earth to be that exciting visually from the ground. GLOW has focused on the discovery of near-Earth asteroids, and the ones we're particularly interested in, and we've got people like Greg with the Space Studies Institute interested in, are those that are most accessible to the Earth. In fact, a handful of the near-Earth asteroids that are the 5 most accessible are shown here, are, if you want to get material back to the Earth from the surface of the asteroid, it's about 1,000 times easier in energy terms to do it from one of these asteroids into low Earth orbit if you use aerodynamic braking than it is to get that same pound of material, say, from the ground up into Earth orbit. The ratio for the Moon is about 7 to 1. The ratio for the asteroid is about 1,000 to 1. The Moon, of course, is only 3 days away. The asteroids go a lot farther. They only come around from time to time. And so for some applications, asteroids are likely to make sense in the future, and for other applications, the Moon is likely to make sense. One of the things we're particularly interested in is the lunar prospector, because if there is a volatile source of the lunar poles, that's going to be exciting for everybody. I guess I'll take your question, but we need to move on pretty quickly.
Are those orbits that you've got plotted there, and the center point is the sun?
That's correct.
Okay, thank you.
Yes, and the blue orbit is the Earth. The blue circle is the Earth. So where we've been going with the asteroid project is kind of in a parallel direction with the solar sail project, which I'll tell you more about in a moment. We hope to send a solar sail spacecraft to do a rendezvous with a succession of near-Earth asteroids. It finally turns out that the Galileo spacecraft will do a flyby of 2 asteroids, 1 or perhaps 2. However, that flyby is going to be very brief. When the body is only a few kilometers across and you're moving at something like 10 kilometers a second relative velocity, you don't get much time to look at what's there. And so the sail is the one propulsion technique which could visit more or less an indefinite number of asteroids, stopping at each one, going into orbit, mapping it, and so on, going on to the next one. So the life-limiting aspect of a solar sail, rather than propellant, as in most spacecraft, is the critical subsystems, and obviously you'll run to the end of that, some redundant string at some point. Let me go into the solar sail project and just remind you that NASA was pretty heavily into this, principally through JPL in the mid-70s, and a mission was designed to go to Halley's Comet. There were 2 principal sail designs. One was this square sail that's about half a mile on the side, which would actually not be in orbit next to the shuttle like it's shown here. That's a little bit of artist license. The sail at this altitude, at the same altitude the shuttle flies into orbit, about 10 minutes. So we have to get a little bit higher before going on. But we need to be above about 1,200 kilometers in order to sail with assurance. Well, NASA dropped the solar sail effort in '77. There was a big political battle between the solar sail and the Ion Drive people. Make a long story short, they shot each other dead. They both fell down in the OK Corral, and neither project has received nearly the attention that they both merit since then. But many of you probably heard of the proposal to have a race to the moon and Mars, one or the other, they're not sure which, that the Columbus Quincentenary Commission has proposed. Here we see the Nina, the Pinta, and the Santa Maria. Of course, they weren't racing for the New World, but the analogy is good for a certain way. Let me review what's going on in the solar sail race business. The idea really came, as far as we know, from Arthur C. Clarke in a story called Sunjammer, published in Boy's Life in 1964. In 1981, French group, Guy Pignolet, are you in the audience here? He's not here. He's been wandering around the conference. Anyway, he and his group were the first to suggest a real solar sail race as opposed to a fictional one. In 1988, the Quincentenary Commission first got some ideas about racing to the moon. In 1989, they released through AIAA a request for proposals to which we've responded. And so far, the Quincentenary Commission has not had any money to offer, and they've not had a launch to offer, so it's not clear exactly what they're doing, but we're going ahead and we're going to be building our spacecraft, and we expect to be lining up a launch in the next 2 months here. So that's where we hope to be in late '92 or early '93. We've got a lot of work between now and then, but it's beginning to look promising again. The spacecraft that we've suggested for this opportunity is the larger square there. The inner square is the so-called engineering development mission, which many of you have probably seen illustrated in different magazines. So we've increased the size of the sail to 3,000 square meters. We've gone from 2 tip vanes to 4 to give us a little more maneuverability, and we've done a few other things that we haven't told our competitors about, so I'll mention this here. We built a test sail. We have this machine available. It can build sails up to considerably larger, in fact, than the one we proposed. We did a test deployment on the ground of a 50-foot on the side sail, which was designed to validate our construction technique and deployment mechanism. And then those of you who may have been at the Voyager Neptune encounter might have seen the mock-up here. This is a full-size engineering mock-up of the spacecraft bus, that is the part of the spacecraft that carries all the electronics, the computers, communications equipment, and so on. And you can see the sail just beginning to deploy. It's stored around the outside of the spacecraft, and the panels have been blown off. And the triangular thing up in the foreground is one of the 2 tip vanes on the engineering development mission sail. The solar sail race vehicle will look very similar, except it'll have a 3rd and 4th tip vane. Our partners on the project include the Radio Amateur Satellite Corporation, or AMSAT. They have flown now, I've lost count, I think they're up to about 18 successful satellites in Earth orbit. They just launched 4 on Ariane in January of this year. And in fact, the microsat satellites which they've flown are in a sense serving as prototypes for the electronics and communication system for our spacecraft. They're just going to use the same design for our spacecraft, even though the microsats are only about 9 inches on the side. If you remember our bus here, we've got lots of room inside the bus. The reason the bus is that large is because of the storage space for the spars and the sail, and so we're not concerned about room inside for the electronics. Anyway, some of the other partners are McDonnell Douglas Space Systems Company at Huntington Beach. The Jet Propulsion Laboratory is a partner. They'll be supplying a communications beacon and probably some ground support, and they've already given us quite a lot of assistance. The Planetary Society has agreed to put on the promotional program for the solar sail race vehicle. We also have Weber State College in Utah and Utah State University, and a company nearby in Los Angeles called Aura Systems. JPL has built some of the spars for us used in the testing. And in case you all haven't been offered a copy, this book edited by Arthur C. Clarke and David Brin just came out from New American Library called Project Solar Sail. It's a collection of chapters, about half of them fiction, half of them fact, all about solar sailing. If you haven't gotten one, run up to the co-sponsors room, and we've got plenty there for you. They've been going quite well. Anyway, this just came out last month. The proceeds do benefit the project, and it tells a lot about what's going on. We've also signed on with Rochester Museum and Science Center up in New York State. With their Space Arc project, we'll be finding them a ride for their archive to contain digital recording of 6 million pages from students, scanned with the students' pictures, their names, and whatever message they want to put out into the future. And we have not yet agreed, but are fairly likely to fly a duplicate of that on the solar sail spacecraft. So there'll be one in Earth orbit on the communications satellite, and another wherever the sail goes, probably out in the vicinity of Mars. Field Publications, the publisher of Weekly Reader, with which many of you probably are familiar from many years ago, they plan to get the solar sail project into each primary school classroom in the United States and every English and science classroom in secondary school to reach about 45 million students with teaching kits, posters, and periodic updates on the progress of the project as the sail is being built, then after launch during the mission as it goes on. Kind of similar to what they've done tracking one of the recent Antarctic expeditions. So this is roughly our path as calculated by the Utah State trajectory people on our team, leaving Earth orbit, swinging by the moon, and then we go into heliocentric orbit, go a little more than, it's about twice around the sun and get to Mars. We may beef up the performance a little bit on that, but we've aimed for a robust spacecraft a little bit more than speed. This of course is our secret plan. This is what we're really going to fly with the basement. Now what we're particularly encouraged about with solar sails is that for moving large masses where you don't care too much how long it takes, they're the ideal propulsion system. It takes about 1/8 of the mass to get a pound from the Earth to Mars using a solar sail as it does to get that same pound using chemical propulsion. And if you look at this chart, on the horizontal axis is the trip time, on the vertical axis is a reference mission mass to low Earth orbit, where the particular baseline reference that was used in this study, funded by Lewis and done at JPL, was 294 days and about 1,700 metric tons for all chemical propulsion. The same mission, sending the crew by chemical but hauling the cargo with sails, we can extend the trip time out to about 600 days for the cargo and drop and take somewhat more than half out of the mass that needs to be launched into Earth orbit. That's a potential multi-billion-dollar saving when we get ready to send the first people to Mars. So that's one of the directions that we're headed with this project. Well, let's talk about Mars a little bit. This was the Collier's Magazine impression of von Braun's plan back in the 1950s. We've been involved quite heavily in the Case for Mars activity since 1981. The conference was put on at the University of Colorado. And the most important feature of this Case for Mars spirit, if you will, is rather than going to Mars, planting the flag, picking up some rocks and coming home, we want to have people on Mars to stay from the first time that we go there to avoid that, the likelihood of the political interrupt and the sticker shock and that sort of thing. People saying, all right, now we've been, let's come home. We've proved to the world we can do that. And it's been now 20 years since the first time we were on the moon, about 18 years since the last time. So what we have done is sought to demonstrate that, in fact, we can build up the spacecraft to do that kind of very ambitious exploration program at the beginning. This is an Earth orbital facility on which the Mars-bound spacecraft might be built. 3 of them depart from Mars at the same time. The picture is taken from the vantage point of one of the 3. They burn out into heliocentric orbit, link up on their way just a few days out from Earth so that the spacecraft can spin. This gives the crew Mars-level gravity for the trip time to Mars and back, which we think is a pretty important element in alleviating some of the physiological degradation. The spacecraft spins until it gets to the vicinity of Mars, and then we despin the spacecraft, and the crew goes down to Mars in these Mars crew shuttles, while the rest of the spacecraft goes on and just sails by Mars. It does not go into Earth orbit, and the crew only stays in orbit briefly in these spacecraft to finally validate the landing site. They come back on the next spacecraft, which went on the next interval you saw on that schedule chart a little earlier. The crew lands, sets up operations on the surface, including a propellant manufacturing plant which extracts carbon monoxide and oxygen out of the Mars atmosphere, and that's used to get the crew back on their way. You can see the propellant plant there, the white thing a little bit above the base, and then some heat radiators. And that's what we hope to advance the time of. And finally, the President has put a time schedule on. He says before 2019. We think it could be done quite a lot sooner than that. And the next Case for Mars conference is coming up next week in Boulder. They've been over 3 years. And so we'll be quite active at that and looking for other mission architectures to save cost and reduce the risk of getting to Mars. Lest I neglect mention of the moon, I have in one slide about that. We're very interested in the moon as well, but time doesn't really permit covering that activity. The last thing that I want to talk to you about is an activity which is being incubated by the Foundation, but which we hope to spin off here in the not too distant future. Our concern has been that the only Western world's access to space has been on the shuttle. And the Soyuz, in fact, while it's been available occasionally for Western passengers, doesn't fly very often as well. And we find that there are a lot of people who are very interested in carrying people into space. Well, we looked at, and you've probably seen things like this, what could we do? The question was, is it possible with the technology we have today to construct an inexpensive vehicle, relatively inexpensive vehicle, it's not going to be cheap, which could fly off the back of a 747, carry a few people into orbit, and come back again? Well, we did some work on that. The answer is, yes, you could probably do it, but the mass margins aren't there. It doesn't really make sense to do it off the back of an airplane, at least of the size of the 747, because by the time you get into the growth that's typical in an engineering project, you've run out of room and your costs start going through the ceiling. So we looked at doing essentially the same thing in a very different kind of vehicle, one that takes off vertically from the ground like an ordinary launch vehicle. In fact, it looks rather reminiscent of what you just saw in the Mars photos of the Mars shuttle. In fact, the shape is from maneuvering warhead reentry vehicles that have been tested under much more severe heating conditions in the defense program. Were declassified about 10 years ago or so, and there's actually quite a lot of data about this. The conclusions that we reached are that passenger transportation, there's going to be a rather larger demand for that in the 1990s than is going to be satisfiable using the shuttle alone for Western access. Of course, the Europeans have already realized this with the Hermes, or Hermes, as they call it, but that's principally a research vehicle. And we've been looking around, and in fact, the price regime that we're looking at being able to operate this vehicle in is $10 to $15 million per launch. It uses existing propulsion. And at that price, there are people who are paying equivalent prices to launch sounding rocket payloads for 6 minutes in microgravity today. For the price that we would need to charge them to launch their same 200-pound box of equipment on a 2-day mission with part of the crew time dedicated to their experiment. So you all recognize this guy. Our hope is to get Charlie Walker 3 or 4 more flights before his career ends. The 2 vehicles that we've looked at, if you look over on the left, there's a single stage version and what we call a drop tank version, and that's how they stack up against the other vehicles. The illustration is a little deceiving because the base diameter of these vehicles is pretty large. It's 20 to 25 feet, and so while they're their mass is comparable to some of the larger unmanned launch vehicles that lift off. The preliminary specifications are that we require a crew of 2. We can carry up to 5 passengers, or trade that off with about 1,900 pounds of payload. In other words, we can unload seats and load on small cargo. We can reach the mirror orbit or the space station orbit. We've got a maximum acceleration of about 3 Gs, an on-orbit stay time of 2 to 5 days, which is extendable if we're at a station. A call-up time, that is, from when a customer says they want to fly something to when we can fly, of about 6 months. The propulsion off the spacecraft uses the RL-10 engines off the Centaur upper stage on this Atlas Centaur, and the RS-27 engines off the Delta launch vehicle. Both of those engines are in fact reusable. They have been reused a number of times on test stands on the ground. The only reason they're not reused in this application on these launch vehicles is because they're derived from ballistic missiles, and no one was particularly interested in how you reuse a ballistic missile after a nuclear war. So the high time RL-10 engine, for example, has 4 hours on it. We need to operate about 10 minutes to get into orbit. The engines have been operating in one form or another for about 30 years without a single in-flight failure. They're probably the most reliable engines in the world today. And we save ourselves a bundle of development costs. We've looked at some of the ground handling of the vehicle. Some of these are a little bit fanciful, but we can use some pretty simple equipment in order to move it around, because when it is empty, it's pretty light. We have an on-pad and during ascent abort capability, so if we had the kind of problem that occurred during Challenger, we would be able to, we'd lose the vehicle, but we'd keep the crew. The top of the vehicle separates, there's an escape motor on it, it's got a reserve chute in it, plops down in the ocean or on land if we happen to be launching from somewhere other than the Cape. As I said, we can abort just about anywhere during the ascent sequence. So that's what the vehicle might look like, probably pretty close to what it'll look like. The bent cone aerodynamic shape is one that's particularly good on entry, gives us a lot of cross range. We've done some work, principally Jim French, our VP for projects, on the ascent profiles and the other engineering parameters. You can see that we're talking about a liftoff acceleration of 1.3 to 1.5 Gs, maximum acceleration of probably on the order of 3 Gs, so it's about like a shuttle ride. And we've got a number of different strategies of when to fire the engines in order to tweak the most payload out of the vehicle. A few views from the cabin. The windows will probably be a little smaller than we've got in this illustration. One of the principal markets that we would expect to serve is carrying small equipment up to space stations or to operate experiments for a few days' time in orbit. As I said, we can reach the space station orbit. We can also reach the mirror orbit from KSC, from the vicinity of KSC, depending on where Florida Spaceport and so on. We expect to be able to conduct this sort of experiment. And we've also looked at building a vehicle a little bit differently with an EVA capability to do satellite servicing. We sent the shuttle up today to do a servicing mission, and it's a great demonstration of technology, which we appreciate tremendously. But when a shuttle mission costs about $350 million and you're working on a $60 million satellite, the arithmetic isn't quite as good as if we're able to do this mission for under $20 million. So we think there's a market there. On the way back, the reentry vehicle comes in, maneuvers down to a little less than Mach 2 speed, pops some drogue chutes, then a main chute, and we have 2 possibilities for landing. One is a Soyuz-style landing, which has been quite successful, where there's some little rockets at the base of the vehicle. They fire at about 60 feet altitude, or about 50 feet altitude for about 1 second, and they cushion the landing on land. We've also looked at a horizontal landing technique with some kind of steerable cargo chute, so we can steer ourselves into the wind and hopefully come pretty close to zeroing out the horizontal velocity. So we've got a lot of work to do, but the status of it is we've been talking with several investor groups. We've gotten a great deal of interest. We have found less vision than interest, as many of you may be familiar with if you're in the if you're familiar with the commercial space business. We're talking now about phase 1 and phase 2 financing. The total vehicle development cost is a little under $500 million to the first revenue flight, which could come as soon as 1994. It's a long shot, but the Foundation's role is as an incubator at this point. If it's spun off as a commercial project, then the Foundation would be a small minority stockholder that would go off, be its own company, and do its own thing. So that's just a glimpse at what we've been up to for the last year or so. And I think I need to yield the podium to Charlene Anderson with the Planetary Society. Thank you.
I hope none of you came here today expecting Luke Friedman. We got involved in switching talks around, and I got designated as pinch hitter for this segment. I think you're all familiar with the Planetary Society, so I don't think I have to introduce us. As you know, we're a medium-sized nonprofit membership organization, and what we do with our research projects is we search out small, worthwhile projects that, with what we call seed money, might be able to bloom. These are projects that NASA or big government agencies or foundations or usual funding sources might ignore. And some of the projects we've been involved with in the past are George Gatewood's astrometric search for extrasolar planets at Allegheny University out of the University of Pittsburgh, Bruce Campbell's radial velocity search for planets at University of British Columbia in Victoria, Jeremy Tatum's asteroid astrometry, also at the University of BC in Victoria, Diana Rice's research on dolphin communications, which we thought might, if she was able to crack the dolphin code, might be a useful analog for if we should ever detect an extraterrestrial civilization. How would we detect their mode of communications? We helped Don Hutton at the University of Arizona design what was called a Mars ball, which was a prototype for a Martian rover. We funded an in situ propellant project at the University of Virginia to examine how one might take indigenous Martian resources and process them into fuels that could be used on the planet either for a return trip or to fuel a settlement or colony that might be set up there. We've also looked in briefly into what we call the Very Cheap Quick mission, which would have been a quick orbiter to send around the moon to look for signs of water on the moon. But as most of you may know, what we've zeroed in on is Mars. The major project the Planetary Society is doing now is what is called the Mars Balloon. This would be a cooperative project with the Soviet Union and the French Space Agency. It actually has received funding now. A couple weeks ago, the Soviets guaranteed the funding for the Mars 94 mission. This is a mission that will launch in 1994. It will send an orbiter around Mars. A lander will reach the surface. It will deploy penetrators to examine the surface, and it will launch a balloon. Now, what the balloon will do is examine the atmosphere. It will carry several instruments on a gondola, take atmospheric measurements. It will measure the wind, since the wind will be the means that it will travel around the planet. It's based on an idea that Jacques Lamont, who's one of our society advisors, came up with in the early 1980s to explore the Venus atmosphere. And this mission flew in 1985 on the Vega spacecraft that went to rendezvous with Halley's Comet, and also sent landers to Venus and deployed balloons in the atmosphere. Now, in Mars 1994, this will carry a balloon. It started off as 2 balloons, but with the budget cuts and such going on in the Soviet Union, we're now down to 1 balloon. It will be a 10-day mission. We'll carry a high-resolution imaging system that will give us 10-centimeter resolution of the Martian surface. We'll carry an infrared spectrometer, an electromagnetic sounder, and a meteorological package. It will also have a radio relay to send its information back up to the United States Mars Observer, which we hope will still be orbiting Mars. This will enable us to get a greater amount of data back. The telemetry system on the Mars Observer is more powerful than what the Soviets will have on Mars 94. Okay, now, here we have the planet. As you know, it's the most Earth-like of all the planets in our solar system. On the left here, you can see the great volcanoes of Tharsis. You can see Valles Marineris. Mars is the only other planet we know of that has surface water. This is the South Pole, which I think this is probably mostly the residual carbon dioxide cap. It also has on its surface evidence that water once flowed. What you see here are teardrop-shaped islands that we see analogs of on Earth after floods, or sometimes in the middles of rivers after great flows. And it's evidence like this that makes Mars one of the most interesting places in the solar system, and for the Planetary Society at the moment, the most interesting. Here we have a detail of the boundary between the northern and southern hemispheres. At the bottom of the picture you can see the ends of outflow channels from perhaps an era of flooding on Mars. And it's things like this that make us very interested. Okay, now here's an artist's conception of the Mars balloon. Up at the top you can see the balloon itself, which is sort of a long wiener-shaped thing. It's a helium balloon that will carry a coating on the balloon that will, it's an infrared coating so that it will be heated by the sunlight. The gas will expand, increase the buoyancy, and it will take off. During the daytime, it's planned to fly during the daytime. You can see the big blob in the middle is the gondola carrying most of the instruments. And down at the bottom you see the Planetary Society's contribution, this little dangling thing down there. That's the guide rope. That's what we call the snake. Now at nighttime, when the sun goes down, the buoyancy in the balloon will decrease and it will descend almost to the surface. To keep it stable at night, it has to have some sort of a guide rope. When going through the balloon designs, when they realized this, we realized that this could make the Mars balloon a surface probe of Mars. If some part of it had to lie on the surface, why not put instruments in it? So you can see there's sort of a little line trailing off the bottom. That's the Mars, that's the snake, and that is what we're working on and developing. This is pictures of some of our tests from 1987. This was when we were working on a dual balloon design concept. Up at top is a helium balloon, and in the center is what was then going to be simply a Montgolfier balloon, a hot air balloon. The French have been working on the design since then, and has now become a single helium balloon that we work on. Okay, here's tests from one of the things we've been having fun with in the last few summers is going out to the desert to test this thing. This is a prototype of the balloon, or the guide rope. You can see that it's segmented. This segmentation has the technical term of Dixie cup segmentation, designed to make it flexible. It's made of stainless steel sections, as you can see. They're sort of stuck together like a string of Dixie cups. What this does is it gives rigidity to the balloon, or to the guide rope, so that we can mount instruments within it, but it also is the best design we've tested so far to prevent snagging. Snagging is the one thing we really have to look out for. If the balloon snags, it's the end of the mission. The guide rope snags, the balloon goes down. The end. And here you see some tests of it going over crevasse at Lava Lake out in California. We've so far had the snake design has not snagged except on bushes. And since we don't anticipate finding bushes on Mars, we think we might have fairly good luck with this design. Okay, here's a close-up where you can see the segmentation. And you know how we keep fiddling around with designs. If the design keeps changing, we're liable to end up with something that looks like this. But right now, with the design as it stands, the snake will weigh about 13.5 kilograms, or about 30 pounds. About 3.5 kilograms, or about 8 pounds, will be instruments. The instruments are being provided by either the French Space Agency or the Soviets. They are still haggling over it, so we don't know who's going to put the final instruments on. The Planetary Society is responsible for measurements of the angle, the tension, and the speed of the snake. This summer, we're working on what we call our snake terrain engineering measurements, or STEM testing, to come up with some sort of speedometer to stick in the little sucker so we can tell how fast it's going across the surface. If I can back up a little bit. The snake, as it's presently designed, will be about 7 meters long. It will have what we call the rope tail hanging out the back to stabilize its little rear end as it's going along there, the tail hanging out there. It seems to flow more stably. And that will be about 4 meters long. So that's the basics of where we are on the snake project right now. And the the second largest program that we're involved with, it's one of the oldest research programs we have. sorry about that, in the Planetary Society, is our Search for Extraterrestrial Intelligence Project Meta. As you know, there are billions of stars out there in our Milky Way galaxy. And if you are an optimistic sort, the probabilities say that perhaps there's another Earth-like planet out there, and perhaps life may have evolved on that planet, and perhaps it even reached some sort of technical level where it might try to be communicating with us. The easiest way to communicate across these distances is by radio. Whoops. And this is the radio telescope we use for Project Meta, which stands for Mega Channel Extraterrestrial Assay. It's now up and running at the Oak Ridge Radio Observatory of Harvard University in Harvard, Massachusetts. This is our dish. It's an 84-foot dish. The receiver we have on it reads 8.4 million radio channels at once. It's designed to pick up an omnidirectional beacon that might be broadcast from any extraterrestrials that might be broadcasting out there. It's tuned to magic frequencies. Now, these magic frequencies are frequencies that, if we tried to think like an alien, how would we try to broadcast across the great distances? Now, there are certain frequencies that are very quiet, natural frequencies, that if you were to send a signal on this, you wouldn't get a lot of interference from extragalactic or intergalactic noise. One of these is the 1420 megahertz line of neutral hydrogen. Another one is the 1667 line of the hydroxyl radical OH. Now, these two lines represent the dissociation products of the water molecule. Now, trying to outsmart these aliens, we thought, well, since we're a water-based life, perhaps they would be too, and perhaps to broadcast on the frequencies of these dissociation products would be a good place, or would be a good thing to do if you're looking for a similar life form. So the meta we have compensates for Doppler-shifted signals. You know, a radio signal, when it's broadcast, suffers from the same Doppler shift that the light from galaxies do as they're receding from us. So you could have Doppler shift from them going away from us, coming toward us. You have Doppler shift from the Earth's revolution as we go around, and the meta receiver we have now can compensate for this. It's up and running 24 hours a day. It is the most powerful continuing search for extraterrestrial intelligence operating in the world today. It picks up maybe half a dozen suspicious signals per year, but so far we haven't been able to get any repeats of the signals. And in order to ascertain that this would be a true extraterrestrial signal, we would have to pick it up at least once more, and I'm sure we'd observe it many, many times over, and so far we haven't picked anything up like that. This here is the Meta equipment. If you look over on the left side, you can see a cabinet that says Meta Supercomputer. And that is exactly what Meta is. It's a supercomputer designed specifically for one project, and that's the search for extraterrestrial intelligence. Okay, now if we pick up a signal, this is what we would expect to see on Meta's little screen, and that's what we've picked up, a few that look like that, but none of them are repeated. So what we're doing is we are expanding our search. These are the telescopes of the Radio Astronomy Institute of Argentina. And we have just duplicated the Meta equipment and shipped it down to Argentina. And on Columbus Day this year, we are planning to switch the thing on and expand our search to the southern hemisphere. This will give us complete coverage of the sky visible from Earth and more than double our chances of finding a signal. So we're very excited about this, and you read the Planetary report. You should keep looking for updates on how the program's going. And if I may quote from Paul Horowitz, who's our principal investigator on Meta, we're light on our feet, and we continue to hatch new and evil schemes. And we're looking at new proposals for even more powerful signals. We're hoping to do this with the drop as microelectronics prices continue to drop. We're hoping to be able to expand this program for about the cost we have spent so far on building the Meta program, which is in the realms of a couple $100,000 compared to, say, a NASA search, where they are up into the several millions of dollars. But that isn't the Planetary Society's way of doing things. So we're still out there plugging away. Perhaps the signal might come from a world such as this. I mean, who knows what life might look like on other planets. And we are also looking for research projects that have to do with this planet back here. As you may know, the Planetary Society has just broadened its focus to include the study of Earth as a planet. And one of the things we are starting to assiduously look for are research projects along the same lines of the other ones we've supported that have to do with the study of Earth. And that's it. Excuse me, I forgot that I brought a short videotape to show if you would like to see why we call this thing snake.
This is the drag rope payload.
I don't know if you can see this, but this is a test from a hot air balloon. You can see the snake dragging on the ground over here.
Unfortunately, I myself looking into the sun a little bit. Payload on Mars will very easily approach lava.
In these balloon tests, we tried different configurations that had that were suggested by other research groups. Some of them were point mass things, which would have been just like dragging a little camera, a little box of instruments, and those snag real easy. What you see here is just a helium balloon. Now this little doohickey here were the original specifications given to us by ICI, the Institute for Space Research in Moscow. This is what they were planning to do. As you can see, it has a slightly rough ride across the surface. It also snags easily.
Consider shaking the wood. Feelings got stuck in the canals.
We're essentially cheating, but I think it's better to do it that way than it is to saw on the rope.
Watch it unlock. Yes, I gotta look at that balloon sink.
This is how it will travel across the Martian surface at night.
Frosting the snake
How much
tail.
did that box weigh?
How much is the what?
How much did that box
Did the
weigh?
box weigh? I don't know how much the box weighs. See, the nice thing about the balloon is over its 10-day mission, it will rise and land 10 times. We'll be able to sample the soil in 10 different places. Now, this is the snake, the segmented Dixie cup design. As you can see, it goes easily over crevasses, up and down slopes. And the only problem we've had, as I mentioned, is that it does snag in bushes.
Moving smoothly. As you don't know.
Do you guys want to ask us any questions? Yeah?
One of your slides, I saw what looked like a little fifth wheel hanging off the back of the snake. Now, is that the ground speed indicator?
That was an early idea for how to build a speedometer, but that little sucker stuck. So we're looking for new ideas now.
When's the launch date for that?
I don't know the month, but it'd be in 1994. So it's coming right up. Yeah?
Are you planning on testing that in volatile environments, weather conditions?
What we've been trying to do is test it in conditions as close as possible to what we think we might find on Mars. Now, do you mean like in strong winds?
Right, storms.
Dealing with the strong winds is more a concern of the French balloon team. People are going to be designing the balloon. We're responsible for the snake. The design that we have now is pretty durable. As you can see, it's made out of stainless steel, and we anticipate that it will fare. The balloon will probably get trashed before our snake.
What about if that goes on?
Well, that would depend on what the ground is like. It's the snagging with little objects, with crevasses or rocks or something on the ground that we're concerned about. So what the slope of Olympus Mons looks like. It might be fairly smooth, easy to traverse. We don't know. Yeah?
Is a hot air balloon close to
You mean the air balloon? It looks like it's going to be easier to fly the helium balloon. It will be a hot helium balloon because the helium inside will be heated by the sun and will expand to increase the buoyancy. We just don't have the helium air system right now. Yeah?
Why is it only a 10-day mission? Was the helium moving out?
That's the estimated lifetime of the balloon, and it could, helium, loss of helium is one of the components in deciding how long it will live. Okay.
Mission of Civil Air Patrol, one of the three main sections of our job is aerospace education, not only for our members, but for the general public as well. Civil Air Patrol personnel will go out and speak to local civic organizations and try to provide aerospace education for the general public. But a lot of what we do involves actually working in the classroom. And it could be something as simple as being invited by a classroom teacher to come in and speak to her students on a particular topic. For instance, Captain Chester's been out just in the past couple of weeks speaking to specific classrooms on shuttle programs. We have a large, diverse amount of information that we have available, and we have worked to make it available to teachers to support what they need to do. The new California Science Framework, while it does not mandate aerospace education in the public schools, does make it a local school option and strongly suggests that it is something that all schools should follow. In that vein, in order to be prepared, we have, starting at the elementary level, we have activity books for young people, and we have single concept learning packets that a teacher could take the information out of and use in her classroom as appropriate, depending on the grade level of the students involved. And some of these activities start down as low as primary grades. And we are strong advocates of primary grade aerospace education. Aside from Civil Air Patrol, I am also a regular working first grade teacher. And I do all of this in my classroom with my first graders. And it has worked well. I've had successful completion of first graders in orbiter naming project. I have first graders growing space tomatoes right now. We have always been actively involved in the aerospace education component of what's happening. Moving up to junior high, we have a complete textbook program that is available, something that we use with our own cadets, but is usable in a regular public school classroom. There's 6 chapters in this book called Horizons Unlimited, and it covers from aerospace history all the way through to the aerospace community of the future. This book is currently being revised. That's something that National Headquarters does frequently in order to maintain the usefulness of the text and to make sure that all of the material is valid, relevant, and is up to date. That book is available with a study guide and a teacher's, instructor's guide as well. For high schoolers, we have a book that was developed several years ago for ROTC programs and is now in its 3rd edition. It's called Aerospace: The Challenge, and it goes into more depth than the Horizons Unlimited for the junior high students. It covers the same range of topics from the history of aviation and aerospace on through to what's coming in the future, just in more detail. This is the newest publication, just out less than a year, I believe. Many of the information packets and things that Captain Chester showed you are available free to teachers. There's an information bulletin and an order form that you simply need to attach to a piece of school letterhead and send to the address on the brochure, and you can receive most of these materials for free. The textbook does have a cost involved, and we also have for 4th through 6th graders, although it is adaptable for younger students if you choose to do the work necessary to adapt for younger children, a program called Falcon Force. It covers the same range of information from the beginning of flight through wind, through how airplanes work. It ties the aviation and aerospace components that it covers into various curricular areas like art, reading, science. It tends to be very intracurricular, and it works well across the curriculum. It's targeted as a learning center type program for 4th through 6th grade students. It does work in lower grades with more directed teaching from the teacher, and I would presume that it would also work at higher grades. Most of my area of expertise is dealing with 1st graders, and I can only tell you from experience at that point. We feel that a firm commitment to the goals of aerospace education for all students. We believe that the material we have available is helpful to teachers, and it covers a wide variety of things in order to hit the areas that you would like to cover in your own classroom. It certainly is supplementary to your regular program and supportive of the things that you are required by your state framework or by your school district curriculum to include in your day-to-day school program. One of the neat things about the Civil Air Patrol program is the availability of people to come into the classroom to provide assistance for the teacher if that were to be suggested. And that's one of the things that we're really proud that we have personnel who are able to do that and are able to bring their areas of expertise into the classroom for our children, so that even if we have a teacher who feels that this is not his or her very finest knowledgeable area, something that they don't have a great deal of expertise in, we're able to come in and say, we will support you. We support young astronaut programs in the local public schools. In some instances, we have cadet members of Civil Air Patrol who run young astronaut programs for younger children in their local school systems. And on a lot of levels, that's a really supportive thing, because not only are the youngsters getting the benefits of the Young Astronaut Program in the science and the math education and the opportunity to learn about aerospace development, but our cadets are also getting a chance to reinforce their own knowledge and to extend what they know by working with younger children. So that really is a program that really has a lot of benefit for everyone. And again, that's something that comes into the school at virtually no cost. We've tried to not set up programs that are expensive or difficult to incorporate or unwieldy in terms of the things that we know teachers are already required to do in their own state frameworks or in their own district curriculum packages. If you are a member of Civil Air Patrol, we have aerospace training beyond that, the training that is involved specifically with working with cadets or working with seniors or working on the external aerospace education mission. So at all levels, we do seek to provide education and support for education for everyone who's interested. I think that briefly covers it. If there's any questions, I'd be happy to try to answer them for you. Yes, ma'am.
How broad are your publications? Is it pretty much in the U.S. space program, or do you get into other sciences, life sciences, or are you pretty much aviation, aerospace oriented?
It pretty much stays aviation aerospace oriented. It does not, especially for the younger students, it does not move out into the broader areas that you're speaking about. Although in the high school textbook, it certainly does begin to move in that direction, more so than the elementary learning packets would. The elementary level, we're concerned mostly with introducing children to what aerospace is, how they are part of the aerospace community, what kinds of aerospace careers are available to them, how this whole aerospace field fits into what life will be when they are the people who are running society, this kind of thing. We use support of NASA programs in the schools. The orbiter naming is one of them. We have a lot of units involved with the Space Seeds program right now. We don't tend to say we're only aviation, but for the most part, we tend toward that more generalized category. Anything else? Thank you very much for your time.
Good morning. I'm Luann Mulbecker from the Challenger Center. I am not Doug King, president of the Challenger Center. I'm assistant to the president. And I've met many of you over the last few days. On Saturday, we presented we were responding to President Bush's challenge on how are we going to become #1 in math and science. And we proposed some general approaches, some strategies that we think are critical to even attempting to meet that goal. So today is our chance to show you what we're actually doing, how we are implementing those strategies. So this is the Challenger Center for Space Education. We are very much proponents, of hands-on teaching. So I'd like to take a step closer to the logistics of this conference. I could not put you all through a simulator. I am going to use a video for the first 5 minutes, so it's a step closer to getting you into it. That will be a general introduction for those of you who may not have known of Challenger Center, but even if you have, I think a lot of you know of maybe our most visible parts, but not everything that we're doing. Then I'll give you the reality, where are we now, where are we heading in the future. Okay, I'm going to start this so I can get the light.
January 1986. The Challenger mission is to explore, to expand the boundaries of human knowledge, and to teach. The Challenger crew will inspire an entire generation to reach for the stars. But tragedy cut short the mission, leaving its goals unfulfilled. As a nation mourns, the families of the Challenger crew commit themselves to a vision that the educational mission their loved ones valued so highly would continue, that it would serve the nation as they did. That vision is Challenger Center. The Challenger Center serves as a catalyst for a new approach to hands-on learning. It teaches teachers and motivates children in the critical areas of science and technology. It is fast becoming a creative force on the educational landscape, an agent for change, and a source of innovative programs. Challenger Center programs rely on children's fascination with space to motivate them to learn, to spark their creativity, and to inspire them to pursue paths of discovery. With space as a theme, the Challenger Center teaches youngsters to think in new ways, to solve problems, and to work in teams. As crew members on a simulated spaceflight, students catch both the spirit and the challenge of scientific investigation. They see why math and science, among the most important yet least popular subjects in American schools, can open the way to exciting, productive work and prepare them for the highly technical society they will live and work in as adults. Because far too many American students abandon math and science before they even get to high school, Challenger Center programs focus on the middle school years, when children often set their own internal compasses for life. And because teachers touch the lives of thousands of students, Challenger Center focuses equally on their work, offering workshops with master teachers, innovative classroom materials, satellite teleconferences, partnerships with existing science centers and children's museums, giving educators not only the tools for effective teaching, but the encouragement and inspiration that brings new vigor to their vocation. October 1989, the first school-based Challenger Learning Center in Prince George's County, Maryland. Today's crew has prepared for their flight using specifically designed classroom materials. The team is ready to launch the computerized voyage on the simulated flight deck, while their team members in mission control stand ready to assist. As in any space mission, success is the product of both team effort and individual problem-solving skills and responsibility. This simulation is no different. Problems arise for which the children, working together, must find an answer. Solutions come from search and discovery, the most powerful kind of learning method. The Maryland site joins the prototype at the Houston Museum of Natural Science in the growing Challenger Center network. With 23 sites becoming operational in the next 2 years and over 75 additional applications in hand, Challenger Center will soon inspire hundreds of thousands of students across the nation. The next phase in the Challenger's own future is a flagship facility in Washington, D.C., an exciting venture now in an advanced planning stage. The flagship building will become an international forum for space science education, linking Challenger programs across the country and around the world, and offering visitors state-of-the-art simulations, exhibits, and teaching demonstrations. For young minds, space opens up a dialogue with the future. Few Challenger Center students will become astronauts, of course, but because of this experience, many will seek to become scientists, mathematicians, or computer experts. Challenger Center, empowering teachers and inspiring youngsters, giving our children a new understanding of the value of math, science, and technology, and a new sense of themselves, of what they can accomplish, and how, as citizens of tomorrow, they can contribute productively to the society in which they will live. The dream, the mission, is real. Yet there are many stars still to reach, and a whole nation of youngsters with dreams for the future. With your support, the Challenger Center can help make their dreams reality.
Thank you very much. Okay, that's an overview of the program. So let me tell you now what really does exist. We are a nonprofit educational institution. As it says, our goal is to provide experiences to students to capture their interest. We are not teaching science and math concepts necessarily, as much as using space as a motivational tool. We're also teaching team problem solving, communication, using hands-on learning. We were founded and still run by the families of the Challenger astronauts, but that really is our history. We have got to be remembered for what we really are, what our results are. This year, 1990, we will touch over 400,000 students and 5,000 teachers through four main programs. The learning centers, those are where students come and fly simulated space missions. That's probably the most visible and the most dramatic part of Challenger Center's program. Right now, 4 of those are in existence. Prototype in Houston, second was in the Houston Museum of Natural Science. Second is run and operated by a school system, Greenbelt, Maryland, a suburb of Washington, D.C. Third opened in Tampa. Fourth is in Dayton, Ohio. By the end of the year, we will have 8. Every day, 200 students are coming through these centers and being touched by space, by seeing how they can fit into the future. Not necessarily even in space. How do they bring that down to life here on Earth? By 1991, we expect 20 centers. We have applications for about 75 right now. Our goal is 50 within 5 years. And if you multiply that out, each learning center has the capability of reaching about 20,000 students per year. So that's 1 million students per year coming just through the learning centers. Our second program, as we said, reaching students, but we also need to reach teachers because they reach many more students. And the main focus of that program has been our teacher workshops. This is a set of material that we put together last October. Okay, it is a 1-day hands-on teacher workshops that are given by the Teacher in Space finalists that merged with Challenger Center. So there's 100 master teachers all over the country, in fact all over the world. Our first workshop was given in Seoul, Korea. Our second one was in Omaha, Nebraska, and our third in Frankfurt, West Germany. So these have been given. It's in a mission sequence, the idea of teachers also benefit from the hands-on learning and the motivation of actually, so not just concepts, run them through the missions as well. They're multidisciplinary. People that are interested in attending workshops should contact our national office, and then we funnel that back through our national faculty, and then we'll be in the process of adding more teachers that can give them. We also have a teleconference program that we initiated last January. Our first teleconference, we were told by experts at NASA that if we reached 100 sites, we would be successful. And we reached over 900 schools, at least one in every state, 200,000 students that pre-registered for the teleconference. They not only, this was interactive, they were able to call in and interview Michael Collins, Apollo 11 astronaut Michael Collins, and we sent out curriculum packets beforehand. So there were pre-activities, there were hands-on activities, they were measuring the size of the image of the moon on the screen so they could figure out how far away they were from the moon. They were timing things, hands-on. So each of those programs are on a continuum of maybe the dramatic impact, but we can reach more students. So we're trying to come up with vehicles that can reach the students that are not normally getting reached, the ones that would not think of coming to space camp, the ones that don't think math and science are for them. We're trying to bring that out to all of them. So if you remember nothing else about Challenger Center, I guess our key characteristics are we use space as a motivational tool to teach, to inspire students, to also inspire teachers. Hands-on, teamwork, communications, multidisciplinary. We are not doing this alone. We're not trying to say, gee, Challenger Center has this great answer. We're just a piece. In our workshop materials in the back is a resource section, and it lists Civil Air Patrol and says the type of materials they have, and Young Astronauts Program and different periodicals. We're not going to accomplish what needs to be done, as a solo effort. It needs to be done together. And I mean, that's how we look on things. In fact, I need to mention to all of you this morning, we decided that there would be an education chapter. This is not Challenger Center, I decided to go off on a tangent. But the whole point of that, again, is network building. So if you have any interest in that, that can serve, again, as a clearinghouse. We're all doing things that are reaching out to teachers and students, and we need to do them together. And our programs are aimed at an early age. I think that's enough because we have limited time here. If there are any questions, I'll take one or two and then pass it on to my next speaker. Yes?
How do you establish a Challenger Center? What is it called?
Okay. Challenger Learning Centers are established, the ones that we've got now, are put in science centers, in museums, school districts. So what it takes is an organization that is interested in running it. Challenger Center nationally does not run these. We use the expertise and the relationships that are already out there. What it takes to establish it always is a coalition of business, government, the educational community, and the science centers getting together. I mean, the best example of success, our latest learning center in Dayton, came about because Jim Rowley, who is one of the 2 teachers in space from Ohio, came back from this conference we had when we put together this last August. Came back, and you know, he has the potential of getting publicity because of who he is. An editorial was written. The school superintendents came to him. I mean, so he had the benefit of, they came to him. Within 2 months, they had the funding. It asked how much it cost. To establish a center typically runs around $300,000, okay? That buys you the simulation equipment, the curriculum materials, the training and installation. And then the organizations or the coalition also operate it. So then there are operating costs as well. It's interesting to see as we go into different, depending on who you're talking to, I mean, that, for science centers and museums, that is well within the range of the price per square foot for this type of environment. And it's really not a problem depending on who you get involved. In Cleveland, I'm trying to establish one. We have a number of organizations that have just gone out and you just start telling people about it. You've got to get the right people together. Okay. We also help in coordinating, fundraising, coordinating, doing the talking. Okay. Any other questions quickly so I don't hog all the time? Okay. Thank you very much. I've got some literature and I'll be around still for another hour or 2. Thanks.
Hi, I'm Ted with the Association of Space Explorers. I think I have about 4 minutes to tell you about the Association of Space Explorers and give you an idea of what, I sense there's some teachers in the crowd, give you an idea of some of the resources we have available for y'all. Just briefly, the Association of Space Explorers was the idea basically of Rusty Schweikart. He was working with some individuals from the Staehle Institute, Soviet American Exchange Program up in the Staehle Institute, as you know, is up the coast here in Big Sur. They have a Soviet American Exchange Program. In 1982, they got together and the director of the program asked Rusty, are you interested in researching parapsychology with the cosmonauts? And he said, no, but I'd be interested to see whether they shared any similar experiences. So they worked together and all that resulted in the first Congress of the Association of Space Explorers in 1985. And they've had subsequent annual meetings since then. The question became, well, okay, now we have an association of astronauts and cosmonauts, people who have been in space, what do we do? With that, they set themselves a series of goals. The goals are to promote, basically to bring together those people who have been in space, to promote international cooperation in space, to promote the use of space and space technology for the benefit of all people, to spread understanding of the historic significance of individuals going into space now, humans going into space, to facilitate public awareness about the achievements in space exploration, and to communicate to the world the experiences of those who have been in space. So I won't go into the challenges of maintaining an organization that we've had. There's been a question of getting people to participate. It's been a question of developing communications between the astronauts and the cosmonauts. And it's been a question of building understanding and trust between the astronauts and cosmonauts. In order to fulfill the goals of the association, there's been a variety of projects that the association has undertaken. The primary one so far that's very visible is the Home Planet book. Those people who are teachers here and who have classrooms, I can recommend this just having in the classroom and maybe taking a quote a day and a picture a day and taking 3 minutes to discuss it and saying, what does this mean to you? This person has seen our Earth from outside, and a lot of these quotations are very poignant in terms of what it means to really look at our home from outside, and that often lends an interesting perspective. We've just, as far as education goes, we have a variety of levels on which we educate. We seek to educate each other in terms of the astronauts and the cosmonauts about each other's experiences. We have exchanges between astronauts and cosmonauts. We seek to educate political leaders about the values of certain types of policies, like for example, our first love within the organization right now is to develop a universal space rescue program such that all the or all the space programs will have compatible docking, et cetera, procedures so that we can effect a rescue. In fact, right now there's some question about the Soyuz, whether it's in a position to be able to return to the ground or not. And also right now we're developing allegiances with international organizations such as the International Astronautical Association and the International Astronautical Federation and the Committee on Space Research, which are primarily scientific organizations and engineering and et cetera associations to facilitate information exchange between people on that particular level. Just in terms of some of the resources that we have available for the educational community, we have a copy of a teleconference that Rusty Schweikart did on video, a la Last Speaker, when a lot of people, it was an interactive satellite video, when a lot of young people were communicating with him, asking him questions, and he was answering those. We have a new video, which is kind of like a video version of The Home Planet. It's called Planet Earth. It was produced by a fellow named Mickey Lemley in New York in association with the United Nations. That's also available. We have available a tape, an audio tape, and a video based on Rusty Schweikart's talk, No Frames, No Boundaries, and it talks about his personal experiences going around planet Earth and seeing that there are no borders, and that what we do over here affects what we do over here on the planet, because the environment is clearly all integrated. And we also, in terms of one more available product, the United Nations recently sponsored with the Association of Space Explorers a program on Earth Day 1990, and it was produced by the United Nations Environmental Program. We had 40 astronauts and cosmonauts come, and a lot of them shared their impressions of what it is to look at the Earth from space and how we must protect her from the own harm we're doing. So those are some educational materials that are available. I can speak, if there's interest, more about challenges of the association and what we're doing within the organization. Also available from the association are annual reports. This is the most recent one. We had a conference in Riyadh. We had a special conference about space rescue at Riyadh, and for those people who are more at the high school level, we have proceedings of that conference which is a series of papers delivered at the conference about various aspects of the question of universal space rescue. We continue to push our politicians and legislators to effect that. I think my time is about up, and I imagine it would be probably appropriate to get any questions if there's any specific interest about the association.